This presentation will be on the floating point representation of numbers. We will review fixed point numbers before we move on to floating point numbers. Fixed point numbers have a set of bits to represent the whole number and another set of bits to represent the fraction. So just like in decimal, where the fractional bits are negative powers of 10, so if 3.14159, that first 1 is the tens place, the 4 is in the hundreds place, the 1 is in the thousands place. These are negative powers of 10. Same thing applies in binary, except the powers are of 2. So after the dot, that first 0 is the halves place, the next is the quarters place, and then the eighths place. So the negative powers of 2, starting with the point, there are 0, 2 to the minus 1, 0 halves, plus 0, 2 to the minus 2, 0 quarters, plus 1, 2 to the minus 3, that's an eighth, and so on. If I take a number like 98.61, if I take the whole number, I can get the binary representation of the whole number using an algorithm where I repeatedly divide by 2 and take the remainder, and then those remainders are my binary number. So 98 divided by 2 is equal to 49 with a remainder of 0. So that 0 is the first digit that is to the left of the dot, the first number in the whole numbers place, the ones place, if you will. And then 49 divided by 2 is 24 with a remainder of 1, so that 1 belongs in the twos place, and we repeat and repeat until we're out of the number. The algorithm for the fractional part is to take the fractional part, in this case 0.61, and repeatedly multiply by 2. So 0.61 times 2 is 1.22. That 1 is our first digit of the fraction, and so that is our halves place. And then we have 0.22 times 2, and we get 0.44. That 0 is our second number, the quarters place. 0.44 times 2 is 0.88, and that 0 is our eighths place, and so on. So we are, in both cases, and previously and now, we are building up our numbers following this algorithm from the dot outward. And then the question is, when do you stop? Well, in a fixed point representation, you will have a set number of bits for the fraction. So you stop when you've gotten sort of all the bits. So if there were 8 bits for the fractional part, you will stop after 8. If there were 16, you'd stop after 16. Just another example, if we take the number 123.456, then let's take the whole number, the integer part, and repeatedly divide by 2. 123 divided by 2 was 61 with a remainder of 1. That 1 is our digit in the ones place. 61 divided by 2 is 30 with a remainder of 1. That 1 belongs in our twos place, and so on. We can also do this on the calculator, so find your calculator. Get yourself into the programmer view, and then in decimal mode, enter the number in decimal, and then you can either look at the binary, which is displayed automatically, or put yourself in the binary mode if you want to copy and paste the number. And one thing we'll need to pay attention to in a fixed point number is, are we using up all the bits or not? So in this example of 123, we see we are using 7 bits. If we were using 8 bits for the whole number, we would need a leading 0. If we were using 16 bits, we would need 9 leading zeros, etc. Let us continue with the fractional part of this example. So 0.456 times 2 gives us 0.912. So that 0 is our digit in the halves place. And that makes sense because 0.456 is less than a half, so we are expecting a 0 in the halves place. Then we take the 0.912 and multiply it by 2, and we get 1.824, so that 1 belongs in our quarters place, and that makes sense. 0.456 was less than a half but more than a quarter, so we're expecting a 1 in the quarters place. And we repeat this process. We can check our process by bringing up the calculator, going into binary mode, and entering the fraction that we found and finding the corresponding decimal. Then we can copy and paste and take that decimal number over to scientific view. So you will lose the number if you just go to scientific view. So you need to copy it when you're in programmer mode, go to the scientific view and then paste it in, or just remember it and type it back in. This check relies on knowing how many bits that we generated. In this case, it was 7. And so we are going to take that number that we just found, 58, and divide it by 2, raised to the 7. And finally, we hit the equal sign and we get a fraction. It will not be exact in most cases. So we started off with 0.456, but our 7-bit representation corresponds to 0.453125. So we stopped at 7 bits, but the number did not naturally terminate at 7 bits. It's just that we stopped. That's why it's not exact. We can turn this check around and use it as a way to find our binary string and replace the repeatedly multiplying by 2 algorithm that we started with. So we take the 0.456 and we multiply by 2 raised to the number of desired bits. And so we were working with 7. So we will do 0.456 times 2 to the 7th. We will get 58.368. We're just going to take the whole number, so 58, and then we're going to represent that in binary. We see that that uses up 6 bits, but we were looking for 7, so we realize we need a leading 0. And again, this makes sense because the fraction was less than a half, so we're expecting a first bit after the dot to be the halves place, and this 0.456 is less than a half, so we're expecting a 0 in the halves place. So if we set aside a certain number of bits for the whole number, and another set of bits for the fractional part, we are doing what's called a fixed point representation. The point, that dividing line between where the whole number is and the fraction is, does not change. It is fixed in place within the number. So we're going to move from fixed point representation to floating point representation, and that is going to allow us to represent a much wider range of numbers. We're going to have much bigger numbers and much smaller numbers, and it's going to be like scientific notation. Recall that scientific notation is used to represent very large and very small numbers. For example, Avogadro's number is 6.022 times 10 to the 23. This is a large number. Or the fundamental charge is 1.602 times 10 to the minus 19 coulombs. This is a very small number. Let's recall how scientific notation works. Let's take a number, a somewhat large number, 12345.6789, which can be represented as 1234.56789 times 10 to the 0. 10 to the 0 is 1. I'm multiplying by 1. I'm not doing anything. I can move the decimal place once to the left, 1234.56789, and multiply by 10, or 10 to the first. I can move the decimal place another position to the left and multiply by 100. I can move another decimal place to the left and raise the power again. And so I keep moving the point and raising the power of 10 until I get to a point where there's a number, a single digit, dot, and the rest of the number. That's our rule for scientific notation. 1 digit, dot, and the remaining digits times 10 raised to some power. We can play a similar game for small numbers. So let's take 0.000012345 O's and then go to the next line and go 0.00004 O's 1234 times 10 to the minus 1. This is the same number. Or 0.0001234 times 10 to the minus 2, and keep going. And again, our rule is to get the first number to be a single digit, a dot, the other numbers times 10 to some power. In this case, that power is a negative power. So now we're going to move from scientific notation, which is a decimal idea, over to floating point numbers, which are binary ideas. The standards for the floating point representation were developed by the Ieee organization, and the standard is given the number 754. So these are the Ieee 754 standards for floating point numbers. So now we're going to replace our scientific notation, our base 10, with a 2. So instead of saying 10 raised to some power, it's going to be 2 raised to some power. We are binary after all. And then, like scientific notation, where that first number we had a digit and dot and then some other digit, we are going to have a similar goal in our floating point notation, that there's going to be 1 digit and then the rest of the number. And in scientific notation, that 1 digit was not allowed to be a 0, and the same thing will be true in floating point representation. That first digit will not allowed to be a 0. But in binary, we only have zeros and ones, so it will have to be a 1. So let's look back at our example of 98.61. So we start off with a pseudo fixed point representation of 11000010.100111, etc. And if we're going to apply our scientific notation like a rule that it should be some digit, dot, and then the rest of the digits, then we must shift the dot 6 places. And we're shifting it 6 places to the left, so we're making that number smaller. So we must compensate by multiplying by a positive power of 2. So we multiply it by 2 to the 6th. And then we're going to put that 6 in binary. We're not done yet, so that power, that exponent, is going to change before we're done. A floating point number is going to consist of 3 parts: the mantissa, the exponent, and the sign. So let's go back to scientific notation for a second. Avogadro's number was 6.022 times 10 to the 23. The charge of an electron is negative 1.602 times 10 to the minus 19. So roughly, the mantissa is the number out front, or at least related to the number out front, 6.022 in scientific notation. The exponent is going to be related to that power of 10, so it's the 23 in Avogadro's number, or the minus 19 in the charge of electron. And then the number has an overall sign. The charge of an electron is negative, whereas the charge of a proton would be positive. So there's an overall sign. That's going to take us 1 bit. And then there is a representation of the power. In scientific notation, it's the power of 10. In floating point numbers, it's going to be a power of 2. That's called the exponent. And then there's the number out front that gets multiplied by that power. And that is the mantissa, or at least related to the mantissa. So we have some number 1.10001, etc., times 2 raised to the, in binary, 110. And so that number out front is going to be the mantissa, the power of 2, the exponent, and there's some overall sign. We still have some playing to do, but this is the basic idea, the 3 parts: the mantissa, the exponent, and the sign. Like scientific notation, floating point numbers are going to be used to represent both large and small numbers. And so remember that the power can be a negative number. The exponent can be a negative number. So if we had a small number, 0.0000110, etc., then we would, to play our game, move that dot until it followed the first 1, and then to compensate, we'd have to multiply by 2 to a minus 5, to a negative power. So we have to have a way in the exponent of representing a negative number. And we're not going to do, say, 2's complement or something like that we know, but we're going to take a process called biasing. So we are going to use biasing to deal with the fact that the power of 2 might be positive or might be negative. And so before, one of our previous examples, the 2 was raised to the power of 6, but we are not going to represent a 6 by a straight sort of binary representation of 1, 1, 0. We are going to use this thing called biasing. So first we ask ourselves, how many bits are we using to represent this exponent? In a floating point number, it's going to be 8. Remember, there are other things other than floats that are similar, like doubles, and then that will change for a double. But for a floating point number, the number of bits representing the exponent is 8, and that corresponds to 2 to the 8th, or 256 possible combinations. And so now we have 256 possible exponents, and we want to be able to represent positive powers of 2 and negative powers of 2. So we're going to take this 256 and roughly divide it in half and have basically, not quite, but basically 128 positive powers of 2 and 128 negative powers of 2. That's what we're going to work towards in this biasing. We're trying to deal with the fact that we can have positive powers of 2 and negative powers of 2. Now, previously, when we had positive and negative numbers, we took a 2's complement procedure. We're not going to do that. We're going to bias. We could have an overall just a sign bit, like the floating point number overall is going to have a sign bit. But this question of the sign of the power of 2 is a separate matter, and we're not going to use a sign bit. Finally, we're going to use this thing called a bias. We are going to take our power of 2, which could be positive or negative, and then we are going to bias it. We are going to add some number to it so that any negative number, once you add the bias, will end up to be a positive number. Okay, so we said we are going to use 8 bits for the exponent. That was 256 combinations, and roughly 128 for negative and 128 for positive. But we're going to reserve some special cases. So we're going to reserve all ones and all zeros for some special purposes. And so that steals one from each side. So we're going to have 127 negative values and 127 positive values. And so then to turn the negative values into the positive values, our bias is going to be 127. So in a previous example, our power of 2 was 2 raised to the 6th. And now we need to bias that 6. So it's 127 plus 6, or 133. And that's what we will represent and call the exponent. So now let's consider the mantissa. In our previous example, we had a binary number that after shifting was 1.1000101, etc. And our rule is that we should have a digit, a dot, and then other digits. And in binary, that first digit had to be a 1. It was not allowed to be a 0. And in binary, the only thing that's not 0 is 1. Now, the standards were developed in a time when storage was an expensive thing. So why store this digit that's always a 1? So in the standard, in the IEEE standard, you do not store this first 1 because it's always 1. It's going to be implied. So you're going to not store it, and then when you use it, you have to sort of remember that it was implied and bring it back into play. So here are the pieces. There's an overall bit for the sign. There are 8 bits for the exponent, and the exponent is biased by 127. There are 23 digits or bits for the mantissa, and there is an implied 1 in front of the mantissa that is not stored. So when we had our example of 98.61, the overall number was positive, so the sign bit is going to be 0. We are biasing our power of 2 was 6, and then we biased it by 127, so the exponent was 10000101, and then our representation, taking away that implied 1 that was out in front, the mantissa was 10001010, etc. So here we're showing a floating point converter that was found on the internet, and again, this is our example of 98.61. The sign bit was 0, so that is unchecked. Our exponent was 10000101, and so we checks where there are 1s. And our mantissa, again, take away the implied 1 at the start, was 10001010, etc. And so we see that the converter is giving us a decimal representation of 98.60999, so pretty close to our 98.61. And here are just some of the references used to put together this presentation.